Hey, what's going on, guys? Let's do this problem right here. This question is asking what is the cell potential of the reaction shown below at 298 Kelvin. Now let's see how we can find it. To find this one out, we can use two equations. The first one is E is equivalent to E naught minus RT over NF ln Q, right? And the other equation we can use is E is equal to E naught minus 0.0591 over 6 log Q. So the second one is only usable when we have room temperature. Like here we have 298 Kelvin, so we can use this one right here. But for other temperatures you have to use this one. So this is energy constant, temperature, number of electrons in valence half reactions, and this is Faraday's constant, and Q is reaction quotient. Now in this case, in the second one, we only need this one right here. This is actually this one. This is not 6. I don't know why did I put 6 right here. This is N, right? So we have to have this N value and Q. We have to find this one out. We have this one already. E naught, that's provided right here. Now let's see how we can find the N. So N value is the number of electrons in valence half reactions, and Q is reaction quotient. Now we can calculate Q first. To find the Q, we use this equation, that is product over reactants, and here we have solid. So whenever you have solids and liquid, you shouldn't include in this equation. So here we are only going to include these aqueous forms. So in the product side we have aluminium 3+. So this is going to be Al 3+ ion, and whatever we have front, we have to power this one. So this is going to be square, and in the bottom we are going to have reactants. We are going to have copper 2+ ion, and the number in front of it is 3, so that's going to be the power. Now let's plug the values. So we have the values right here. Al3+ is 0.1, 0.1 cube, square, 0.1 square over Cu2+ cube, that is 2.5 cube. And if you calculate this one, you should get 6.4 times 10 to the power of -4. So this is our Q value. Now let's see how we can find N value. To find the N value, we had to take the oxidation half and reduction half. So here we have oxidation half, that is due to aluminium. So we have aluminium, 2 aluminium. Maybe I use a different color. 2 aluminium, and then that produces 2 Al3+, and number of electrons we are going to have is 2 times 3, that's going to be 6 electrons, right? So to balance this one, we have to put 6 electrons right here. Now let's look at the other one, that is reduction half. Here we have 3 copper 2+, 3 copper 2+ plus 6 electron again, 3 times 2, 6 electron in this side, and then we have other side we have 3 Cu. So this is our oxidation half and reduction half. And if you look at the number of electrons, we have 6 electrons, 6 electrons. So N is going to be 6 electrons, right? So that's the value we are going to use. Now let's plug this one into this equation. Now let's plug everything. First we are going to have E, that is equivalent to E naught, that is 2 volts. So this is going to be 2 minus 0.0591, and this is number of electrons, that is 6, and then we have log times Q value. So here we have Q value that we found out, that is 6.4 times 10 to the power of -4, and if you calculate this one, if you plug exactly as it is in the calculator, you should get 2.03 volts. So that's going to be the cell potential. Now we have to know what is the difference between E and E naught. E naught is standard cell potential and E value is non-standard cell potential. So here, since we have E naught, the question is asking for non-standard cell potential, right? So that's what we have figured out right here, and this is how we do this kind of problems. I hope you guys find this video helpful. See you next time.